Hello everyone, in this video we will talk about a new topic, Newton-Raphson method. This method is a very well-known method. It's well-known for its fast convergence. If it converges, it usually converges very fast. The problem is still the root finding problem. Given a function of one variable fx, find a value of r such that fr is equal to 0. The assumption we assume that the function fx is continuous and it has a continuous derivative. So for this method, we not only require the function fx to be continuous, we also requires that it has a continuous derivative, which means fx prime is also continuous. So the initial requirement to use this method, we need to have a initial guess about the root. So there should be an initial approximation x0, and it's different from the previous two methods. We don't need to start with an initial interval a to b which brackets the root. We just need one single approximation. So that's why this method doesn't belong to the bracketing method. It belongs to the open method. Then the iteration process, given the approximation xi, which we get from the ith iteration, and how to get the next approximation xi plus 1. The formula is shown here. So xi plus 1 is equal to xi minus fxi over fxi prime. So let me show you how this formula is obtained. Assuming that we have a function okay, and you can see the root is located here. Assume that we don't know where is the root when we have an initial guess that it's at here, right? Assuming that it's not the initial guess, it's the approximate value we obtained in the ith iteration xi. So let me show you how to base on this xi to get the next approximation xi plus 1. We first draw a vertical line which will from the point xi, and this vertical line will have a intersection point with the function, and then at this point we draw a tangent line. We draw a line which is tangent to this function, right? Then this tangent line will have an intersection point with the x-axis, and this point will be the next approximation for the root, so xi plus 1. Okay, so let's see how to mathematically derive the formula for xi plus 1. You can see here, assuming that this angle is called theta, right? Because this is the tangent line, so tangent theta is equal to the derivative of fx at the point x equal to xi, right? So it's fxi prime. And also in this triangle, you can see that the tangent theta should be the length of this side over the length of this side, right? So tangent theta is the length of this side, which is fxi, over the length of this side, which is xi minus xi plus 1. So tangent theta, which is equal to fxi prime, should be equal to fxi over xi minus xi plus 1, right? Then we can multiply both sides by xi minus xi plus 1. Then we can have negative xi plus 1 times fxi prime equal to fxi minus xi times fxi prime, right? So the xi plus 1 will be fxi minus xi fxi prime over fxi prime, right? So this should be equal to xi. Okay, so this is the negative, right? So we have, let me write here. So xi plus 1 should be equal to xi minus fxi over fxi prime. Okay, so this is how to guide the formula and how to do the iteration process. So after you guide xi plus 1, you draw a vertical line, right, which have a intersection point with the function, and then draw a tangent line which is tangent to this function, and this line will have a intersection point with the x-axis, which will be xi plus 2. You can see that xi plus 2 on this figure is already very close to the root. So this method, sometimes it converges, sometimes it doesn't, but if it converges, it usually converges really, really fast. All right, so let's see one example. Perform 3 steps of Newton-Raphson method for the function fx, which is equal to x squared minus 2, starting with the initial guess x0 equal to 1, right? Since x0 equal to 1, then x1 should be equal to x0 minus fx0 over fx0 prime. Just use the formula. So x0 is 1, so it should be 1 minus fx0 f1, which is 1 squared minus 2, over the derivative of fx at the point x equal to x0. So we first need to guide the derivative of this function, which is 2x, right? So 2x at the point x equal to x0, which is 2 times 1. So this should be 1 minus negative 1 over 2. So it's 1 plus 1/2, so it's 1.5. All right, so this will be the first iteration. So let's see the second iteration, x2 equal to x1 minus fx1 over fx1 prime. And x1 is 1.5 minus fx1 is 1.5 squared minus 2 over 2 times x1, so 1.3, right? So it's 1.5 minus 2.25 minus 2 is 0.25 over 3. So this will be 3 over 2 minus 1 over 12. This will be 12, 17 over 12. So this is the result for x2. In the next iteration, let's see, x3 equal to x2 minus fx2 over fx2 prime. So x2 will be 17 over 12 minus 17 over 12 square minus 2, right? So let's use MATLAB. 17 over 12 square minus 2, 0.00694, 0.006944, and this should be 2 times 17 over 12, so it's 30, so it's 2.83. 6944 over should be 0.00. So let me see, 17 over 12 minus should be 1.414216, right? 1.414216, approximately equal to this value. So the exact solution, the root for this one should be the square root of 2, right? So it's 1.414214. And you can see after 3 iterations, we are already really close to the actual root, right? Becomes really close to the root after only 3 iteration. All right. Okay, in the next video, we will talk about the halting condition of Newton-Raphson method.